morning, everyone. Welcome to the show. We're going to start with an explosion. In case of unexpected emergency, that's unlikely. Notice where the exits are on top, 2 exits, and on the bottom, 2 exits. And this show is sponsored by the American Chemical Society, Rochester local ACS section, and chemistry department at St. John Fisher University. Names of presenters are there. The QR barcode is there. You can follow that. It describes the experiments that we will be doing. Also, the schedule, the order of experiments are placed on that website. Just scan that bar. All right, as I said, we're going to start with an explosion. It's going to just signal the beginning of the show. Right, so let's just wait. It will be loud. You can close your ears if you sense it. This is it. The show starts.
So, our first experiment here are our thermite balls. What we have is a ball of aluminum and a ball of iron that has rusted. And when you put these together with enough energy, so let's really give it a go. Ready? We'll try to get it together. 1, 2, 3. Try again. 1, 2, 3. We're trying to go down the line. Ready? You first. One more. Okay. All right.
Thermite is a really cool reaction. It's used to weld railroad ties in place. It was used heavily in World War II to turn artillery into giant paperweights.
Melt tanks.
Melt tanks, yes. Normally this is done with aluminum powder and iron oxide powder. And it takes place because aluminum is more reactive than iron and will take the place of the iron in the iron oxide compound. But it also releases a ton of heat and a ton of molten iron, which is why we don't do it with powder inside, because it generates a ton of heat and molten iron. But this is also pretty neat.
Yeah.
Okay, so that's thermite balls. After the show, if anybody would like to try to make sparks with thermite balls, by all means, you can go ahead. Just watch your fingers.
Hello, everyone. I will happily speak very loudly. Excellent. My name is Joel Monaco, and I'm here to show you the Golden Rain experiment, or demonstration. What I have here is 2 clear liquids, yes?
Did you want the funnel for this?
What?
Did you want the funnel?
No, I think I practiced earlier. We do not need the funnel.
Okay.
One of those clear liquids contains something called potassium iodide. Very colorful substance, yes? This other liquid contains what's called lead nitrate. Very colorful as well, yes? All right, now let's see if I can do this correctly. These 2 chemicals, when mixed, should create something that is... You may. Oh, yes, so everyone can see. There we are. Careful. You know how I'm going to do the thing. All right. Swirling. That was the... It's gold. This is lead iodide, a very insoluble substance at room temperature. However, it's not going to stay at room temperature for very long. No, just for effect. Hot water. Now, this one we had to do at the beginning of our presentation because if I've done it correctly, and I probably didn't, what will happen is it's going to disappear again. Wait for it. And I'll do a little more here. Then, the secret is to not take your eyes off it for the next 2 hours. I'm just kidding. 45 minutes. But now we have lead iodide back in solution. But it's hot liquid. What's going to happen over the next hour as I let it sit here? I've got an assignment for you. Don't take your eyes off of this. Don't watch the rest of the show. You can't watch the rest of the show. You got to keep your eyes on this only. I'm just kidding. You know what you're looking for? You'll know when you see it. No, we'll see something start to form over the next 45 minutes or so to an hour, and it should rain back down to the bottom. So those very tiny little crystals might make another appearance for us as big flaky bits. So keep an eye on that as we do the rest of the show. Ooh, it might already start happening. We'll see. Thank you very much. Golden Ring.
For the next experiment, I need a volunteer. But before you volunteer, listen what I'm going to ask you to do. You don't know. I'd like to donate your drink and see if you're drinking something flammable. Is your drink flammable? Well, anyway, if you have just water or something, let's come here. I need 2 volunteers, okay? You? And in the middle, you are in the black t-shirt. Okay, so come here, come here, feel the whole thing. Just grab this one. This is the water. Let's just turn on the light. Okay. The water is flammable. The juice was not. That's interesting. Does anyone have a different drink? Oh, the juice is also a little bit flammable. And not much. Thank you for volunteering. So the next one is soapy bubbles. Alright, so in this balloon there's a gas, methane, and we're going to make bubbles out of this gas. So this. Alright, let's see if it is flammable. So I'm going to grab this hole and let's see what it does. In this liquid nitrogen, I have a balloon that is shrunk. When I take it out, it's expanding. So that balloon is expanding. Yeah, it's spinning slowly. It's warming up, and the gas, whatever gas is inside, it's expanding because it's warming, creating a little high pressure. Well, it looks like normal balloons going down. So let's convert this balloon into a fuel tank. I'm going to stick a needle inside of it. So this is the sharp needle on one end, and I'm going to stick this needle. It's going to pop. Oh, let's just see, maybe not. Oh, okay, it survived. It survived. All right, so let's just see if we can turn on the light and have a inside is flammable. Guess what kind of gas is it? It is methane, that's right. So what else we can do with that? It's not stable flame. Maybe it's mixed with air. But let's just see if we can make some sparkles. So I'm gonna just blow magnesium powder. Okay.
Okay, so our next demonstration is the self-carving pumpkin. 2, 1.
Hey, you want it?
So, self-carving pumpkin wasn't that great. All right.
Yeah.
That's all right.
Yeah. You save the pieces.
We'll see. Yeah,
We'll finish with a bang.
we'll finish with a bang. All right. So, this is the barfing pumpkin. Hopefully, this one goes a little bit better. All right. So, in the flask right here, I just have the chemicals that are in glow stick. Glow sticks are actually really cool. So it's a multi-step reaction where 2 chemicals mix and they emit a photon of ultraviolet light. That, of course, we can't see ultraviolet light, but the dye in a glow stick picks up that photon of ultraviolet light and it actually gives us out a photon of visible light. So I really think glow sticks are very, very cool. Now, one of the chemicals in a glow stick is hydrogen peroxide. And without the hydrogen peroxide, we really would not see any glow. So I'm going to put a little extra hydrogen peroxide in here. And what we should see is the glow get a little bit more intense at first. And then I'm going to put another chemical in there. And we can get that oxygen to come out in several different ways. We can use chemicals like potassium iodide or sodium iodide, potassium permanganate. But what we use for this is just good old-fashioned bread yeast. Bread yeast has an enzyme in it that will also get this to work. So hopefully we'll get a little bit brighter. A little bit brighter. Okay, maybe not. Boy, pumpkins maybe not doing their thing this year. Okay, let's see if we can get rid of barf. Come on, Barfy.
It's barfing.
Is it barfing?
Oh yeah, it's barfing.
Yeah, it just doesn't want to barf on that. Okay, that's fine. All right. There we go. All right, guys. All right.
Okay, so is everyone ready? Ready. Let's take a look. Okay, so we're gonna mix iodate and potassium iodide. And there's a reaction producing elementary iodine that will turn blue color for the starch. You can read about the experiment description, so let's do that. All of them mixed at the same time. You've heard about the superconductors. They're going to change our Oh, by the way, this is not finished yet. Sorry. Yay! All colors disappeared. So our next experiment is a superconductor, and to just demonstrate what the superconductors can do, you can imagine a train on a magnetic rail, and it does save energy. It doesn't take too much energy to move the train. And in the future, we'll have high-speed trains working on superconductors, room temperature superconductors. But this one works at the temperature of liquid nitrogen. You can just levitate above magnets. And if I push it in that direction, it doesn't go. It only goes in one direction. So the magnetic field is oriented. You can play air hockey with it. And at the end of the show, you can just come and we'll make it a game. You can play with it. So a regular magnet would stick to the surface or will be flipped. But this one is stable. It doesn't flip and it's moving, it's levitating. Okay, well, that's it. So our next experiment is leaking blood. I could ask for volunteer, but I think I will volunteer myself because this experiment is dangerous. Okay, so I'm going to disinfect my hand. And then let's just cut it. You see that? Okay, so let's just cut it.
That's pretty cool.
Okay, well, all right. I'm fine. But what you can also do is, let's just say, to draw the blood. So again, a little bit of alcohol, and then I'm gonna draw the blood from my hand into the syringe. That's what the nurses do, don't they do that?
Very cool.
So, the secret is actually explained on the website. You can see what kind of reaction is that. Next one is genie in the bottle. Okay, so genie in the bottle. Right, so you see that it says genie. We have to trust the label. There's genie inside. And it says do not open. So what should we do? Should we open it? All right. Now just watch for the genie to come out. Come on, genie.
So this next demo is called Barking Dog, or sometimes it's known as Whoosh Bottle. And what we have in these various pieces of glassware is a flammable liquid, methanol. Though that's a little bit misleading, the term flammable liquid. It's not really the liquid that's flammable, it's actually the vapor that it gives off. And what we're going to do is we're going to light it on fire, and we're just going to kind of see the various sounds that the different glassware makes. So we'll start with the smallest one. We have a 250 ml graduated cylinder.
Okay, so be on the lookout here for not only sights but sounds. Not only sights but sounds.
So this one. a whimpering dog.
Same concept, same shape, piece of glassware, but more volume this time. The first one was 250 milliliters. This is 500 milliliters. So let's see if we do see a difference, and hopefully hear a difference.
A little bigger.
A little bigger.
How much?
A little bigger.
It's not scaring me.
No, it wasn't scaring me. That was scaring parts. Okay, same concept, same shape, piece of glassware, twice the volume. I didn't need that. Okay. Thank God you're letting it.
Alright.
Okay. Okay.
Now,
this one's going to be a whistling hyena, I'm sure.
I don't have a whole lot of high hopes for this one, but let's see. Come on, bark. We need a bark.
We need a bark.
We're looking for a bark.
Okay. That was like
Deeper. I don't think we're going to get a bark on this one, but
this one's more of a bottle shape. You said in the beginning this is also sometimes called the whoosh bottle.
The whoosh.
So let's see.
the whoosh.
Let's see if this bottle whooshes. Would you mind if I did this?
Go for it.
Okay. Okay.
Alright.
All right. I should just painted one of these orange. Okay.
There you go.
Okay, so that was a little bit better. I would say that was a whoosh. Those were okay, but a very wise chemist once told me that often bigger is better. So, that one's a little bigger. That one's a little bit bigger. Okay, now, did you guys see the color of those flames? Okay. So did you guys see the color of those flames? What color were those flames? Blue. Absolutely. Okay. Now, this hopefully will be a different color, but you know, as the pumpkin taught us, not everything sometimes goes according to plan. So, let's see. Let's see what we see. Now, this is a much bigger bottle. So, you guys, do you think it's going to be louder or quieter? Let's hope so. All right. Are you sure you don't want to do this one?
Yeah, it's all yours.
Okay. Joel, did you want to do this one? Good. Okay. What color was this one? So that one, what color did you guys see the flame? Green. That one was green, so there's a chemical in there called copper chloride. Copper ions turn flames green. There is a different chemical in this one, although it turned the same color when I put it in there, so that wasn't super promising, but alright, let's see what happens. Alright, what color do you guys think this flame is going to be? Shout it out. Green. Shout out another color. Shout out to blue. Blue. Red, purple, yellow, okay.
Alright, let's see. And the winner is...
FedEx, you showed up, guys.
All right, so hopefully this one will show us why this demonstration is called the barking dog. All right, so there we go. That is the barking dog. It appears that Dr. Vignichenko's nitrocellulose was so perfectly made that the heat from that bottle set off his nitrocellulose, which caused a little hole in the side of the bottle, which then led to this monstrosity. So unexpected, but thank you for everybody for keeping your wits about you, which is actually a really good demonstration point. Notice how when that happened, did any of the chemists up here run around and make things worse? No. No. So we all moved very slowly and deliberately, which is what you should try and emulate if you're in an emergency situation, especially in the chem lab. You don't want your actions to make something that's bad that's going on even worse. So hopefully a little teachable moment. Woo!
I'm awake now.
Oh, I'm wide awake. Yeah.
Okay, our next experiment is peaceful. This is the only peaceful experiment that we have. It's called chemical spaghetti. We have solutions. We will mix solutions. We will make colorful spaghettis. We have blue, yellow, green, and purple color. And those solutions filled in the syringe. So I can have one or two at a time. And what I'm going to do, I'm just going to put them in the solution and start squeezing. So what comes out? That is the spaghetti. So take it out. At the end of the show, you can play with it. So let's have more. How about yellow and what? Green. In the description of this experiment, you will find that some compositions are eatable. You can make them in your kitchen and eat. Not this one, because it's not food grade.
What are we up for next?
So, our next experiment is also peaceful. Let's turn off the light. So, in these bottles, we will produce a chemiluminescent reactions. Okay, that's all.
Good job.
Our next demo here does not have any fire. It's called the rainbow connection. What we have is various indicators which are different colors based off of pH. We're going to see if we can kind of get the colors to kind of go back and forth from color to no color, varying the pH of starting with acids and then add a little bit of base, then add some more acid, and see if we can kind of get the colors to go back and forth. And you'll see why it's called the rainbow connection.
Okay.
All right, want to start with this one?
Yes.
All right, so we're going to add some acid to our first indicator, and not a whole lot happens. But then we're going to add some base. All right. Our next one, acid. Woo! Add some base. Orange. Orange.
Okay, what's orange?
All right.
Yeah, all right.
Our next one here.
That's orange.
Orange.
Orange. Okay. That's kind of grello too. All right. Okay.
All right, let's keep it rolling here.
Let's keep it rolling. Okay. Red, orange, yellow,
Red, orange, yellow, green.
green. Let's see.
All right, there we go. Now we're cooking.
Now we
All right, red, orange, yellow, green.
blue.
Let's see.
I mean, we already did ourselves.
There we go. All right.
All right, there we go.
Start.
Good.
Things are working out.
Okay.
All right.
Red, orange, yellow,
Green, blue.
purple. Thank you for not saying indigo.
All right.
All right. Okay. All right. Those are great colors.
Okay.
Those are great colors. You know what though? I can't see them.
Yeah.
And I'm like blind. Yeah.
Okay. So we got red, orange, yellow, green, blue, purple. All right.
What
So
colors are there?
red, orange. Red. Okay. Orange.
Orange. Try it again.
Yellow.
This is more fun for me than it is for you.
Green.
Okay.
Worked hard on that green. I worked hard on it.
Not hard enough.
All right.
Okay.
Blue.
This is where things started to turn around.
Yeah.
This is it's gotta be hard to see.
All right.
Okay.
And purple.
I can do
I got good hopes on purple. It's gonna stay. I worked hard on that purple. All right. You know what?
What?
I like the colors. There we go. Much better.
That was pretty good. Some late. Yeah.
There we go.
The rainbow connection.
This is going to be the classic demonstration of solubility of a gas. No, I mean, it's called the ammonia fountain. So I have in this jar just plain old water. And I have in this Florence flask nothing at the moment. What I'm going to do is I'm going to put some ammonium hydroxide into the Florence flask. Okay. So we're filling this space in this Florence flask with ammonia gas because this liquid likes to produce a vapor. Do you have a hot glove on us?
Yeah.
May I have it? Thank you. All right, now, the other thing about ammonia is that it is, just one.
Yeah.
Right-handed. These are both left hands. So when we heat this up, it'll produce more ammonia gas. But we don't want to heat it up too much. We're just going to heat it up so that the Florence flask itself really doesn't have any air left in it. Okay? Now, we're not really trying to boil the ammonia. We're trying to get it to vaporize and fill the space inside this jar, flask, with ammonia and push the air out.
There you go, sir.
Definitely. So we're sputtering some ammonia out the top here. So now we're going to carefully flip this upside down and put it into this water. So what you're seeing is the gas that we filled that flask with absorbed water. So the gas that filled the flask is literally sucking the water up into the top container. And we've added some chemicals in there to make it a little bit, well, more visible, but this one seems to have not had enough. And it's creating a little fountain on the inside. And in a moment, if we did it correctly, it'll actually pull air and break the vacuum at the very bottom in this other flask, and then it'll be easier to get apart later. There we go. Now we're sputtering. And in that same moment, it no longer is pink. Demonifying. Thank you very much.
Right, so the next one is virgin nitrocellulose. This is going to be quick powder that is actually used. And it is burning really, really fast. So I'm going to ignite one end, and the fire will propagate in that direction. So see how quick it is. All right, are we ready? Okay, let's do that. That was quick.
That was very quick.
Now we're going to have more experiments with nitrocellulose.
All right. So, Dr. Ivanchenko mentioned that this is kind of powderless gunpowder. In fact, it's another name for nitrocellulose is gun cotton. Now, 200-ish years ago, a chemist by the name of Friedrich von Schoenbein, like a very good chemist, had promised his wife that he would no longer conduct experiments in the kitchen with concentrated acids. Friedrich von Schoenbein immediately forgot that he had told his wife that and started working with concentrated acids in the kitchen. And also, like a good chemist, he spilled it. And what was there to clean up that spill but his wife's apron? So, he takes his wife's apron, so the story goes. He takes his wife's apron, he cleans up the mess, but now it's covered with concentrated acids, so like an absent-minded chemist who wants to get back to his experiment, he hangs it up to dry, and what a better place to hang up your wife's acid-soaked apron than right next to the wood stove. And all of a sudden, the story goes, he hears a whoosh! He looks over, his wife's apron is gone, not a single shred of ash to be found, and Dr. Schoenbein has discovered something wonderful, somewhat by accident, if you believe the story. I have a hard time believing that. Nitrocellulose takes at least 24 hours to make, so I think Friedrich might have been telling a little bit of a fib there. But no worries, because he did come up with something pretty damn Awesome. So Dr. I set off his nitrocellulose with the lighter there, but you can actually set off nitrocellulose with just a glowing splint. So, Mr. Johnson, if you would be so kind.
Yes, sir.
Would you light me on fire? Again? Alright, so nitrocellulose does burn very, very quickly, and without any ash. There won't be any sound from this one other than hopefully a little foom, so you do not have to protect your ears. Go ahead. Alright, so very, very, very quick combustion, which is what we want from anything that is going to perform a launch of any sort for us. So you can see why this is referred to as gun cotton, because you can use it to propel a bullet. All right, so now this is obviously an extraordinarily simplistic version of a gun, but you can hopefully, we've all seen like a war movie, maybe a Civil War movie, where guys are struggling to get their muzzle loader loaded. You've got to put down wadding, and you have to put down the primer, and then the gunpowder, and then more wadding, and then your bullet, which takes a really long time. With gun cotton, several of those loading steps were taken out of the way. So if your army can load faster, they can fight faster. All right, so with just a glowing splint. Okay. Now, that was a relatively small piece. Last year we tried to get up to the ceiling with our last one, but I only had one arm last year, and these guys let me struggle up here trying to aim this all by myself. All right, let's give it a shot. All right, now you guys let me know if this actually hits the ceiling. Let's hope it does. You guys have been an absolutely wonderful audience, so thank you all so much for attending. Before we do our final demo, this is another one that is going to get loud. So, how do we cover our ears? We stick our fingers right in, right? No, we cover.
Okay, we're closing now. So we can explode. Let's couple more. Old technology. This is secret.
Your old standby.
Old standard technology. So thank you for coming, and please grab a snack, and you can stop at the PlayStation and do some experiments.
Hey guys, there's all sorts of neat stuff for you guys to do. There's something for you to make and take. There's something for you to watch. Really, really cool. Something happened. Another really cool thing over here. So it's not over. Now it's time for you guys to come up and be scientists too. Okay? Okay, so come up and be scientists. Come